Okay, welcome everybody. How's it going? Okay, so how did you all find the last assignment? I got a little bit of a clue that there was some question about one of the problems, which I can go over. Were there like general thoughts on it? Okay. A little more difficult maybe than the prior ones. Okay. Yeah, this is maybe we're transitioning. The problems are going to get significantly harder. Okay, than what we're talking about here. Okay. So, but we're here, and we have the group me, and we have the ability to chat about things. It's okay if we don't get them all right? So I think there's a question about how to handle number 5 on the second assignment. All right, so for this, we need to put in a value for P, right? And that's just the value that's given, right? And D, all right, so D, the way I have it set up is that you can put it in centimeters, right? Or you could opt to change it and put it in meters if you like. But for now, let's just go ahead and assume that you're going to put it in meters. Okay? And I guess backing up for this, right? The goal here is to figure out what the stress in this third member is. Okay? So we need to figure out what the force, the axial force in that member is. And we can do that by using the linear equations and the method of joints or the method of sections, and you can do that algebra, which is in the slides for session 3, I believe. Okay, or you can use this code. So if we use this code is essentially using the method of joints. Okay, and it's solving 3 equations. All right, a system of 3 linear equations. And these, so A has the coefficients, okay, X, okay, which is what we're solving for. All right, so we have like an AX equals B. All right, so X is going to be the internal forces in a column vector. And then B is going to be the right-hand side of those equations. Okay, so that's what we have here, and then we solve. All right, for X. The matrices in Python are 0 indexed. All right, so that means that X bracket 0 is actually the first element of X. X bracket 1 is the second element of X, and X bracket 3 is the third element of X. Okay, so as I was kind of trying to explain in the group me without giving the exact form, right? This x2, right here, it says, hey, print x2. That is actually spitting out what the force in member 3 is. Okay, and so you put in your P, you put in your D. It does the calculations for you, or you could have done them by hand. It gives you the force. So now, the next thing is fill in this line of code appropriately. All right, so what is appropriate? Well, I'm looking for a stress, right, in member 3. So what is that going to, what would you put in there? Yes.
You would have X bracket 2.
Yes.
What the area is. So
Yes.
I R squared.
Right. Okay. So this is where it gets a little bit confusing, right? So because I had D in centimeters, okay, and I want to be careful here, what I really should do is I should do D times 0.01. That will give me now diameter in meters, okay? Then we have to square it, and like we said in the group me, square is not caret, okay, in Python. Square is 2 asterisks next to each other, all right? And then we divide by 4, okay, because it's pi d squared over 4. And so, unless I made a mistake, that should be it. That's how you fill in that line appropriately. And then you run it. Okay. So, I don't know, did anyone, what's the value? Would people want to give me some values? We can try it out. Actually, I have to, in order to run this, I have to sign in. Oh, I think, let's see, I am signed in. Let's see if it works though. Okay, so first we'll do this. We run this line. Okay, run anyway. Okay, so I don't know. Anyone want to give me some values?
1305.
Okay, 1305.
Point 012.
Okay, so let me guess. That was 1.2 centimeters, right? Okay, and then I have the D, because I did D times 0.01 here, right? And so then when I hit this, I get 16 megapascals. That sounds about right. Okay. So that's one way to do it. So, you know, yes, it's easy for me to do because I've done it a bunch of times. But as we're going forward, in fact, this particular assignment that's due tomorrow, the problems 4, 5, and 6 are almost the same, but because of the way Canvas works, it's going to generate different numbers to plug in. And so, again, using some type of calculator like Desmos or Python is probably a good idea, because then you've got all the algebraic equations. You just put in the new numerical values. Okay. Any questions on this? Thoughts? Okay. How would you have done this in MATLAB? Because a lot of you are more familiar with MATLAB. How do you think you would have done it in MATLAB? Maybe I should make it bigger because it's a little bit smallish. Any thoughts? Or what would be different? Let's put it that way. If you were to put this code in MATLAB, what would be different? Yes.
Build an ouch.solve.
Yeah, right. You wouldn't have to do that. So what you would probably do is you do like an inverse, okay, of A, right? And then you multiply both sides by that, right? And it'd be a little bit simpler format. Okay, so that's one thing, right? But it would give you the other thing. And what's another thing that would be different? Which we talked about. Would you do x bracket 2? No, right? What would you do? Yeah, and it would be 3 because it's 1 index, not 0 index. All right, so that would be x of 3 would give you that member, the force in member 3, right? And then of course, MATLAB won't like the asterisk, I don't think. I don't know, maybe I've never tried asterisk. Actually, I probably have by accident, typing it twice, you know, and it will give you an error, so you would use the caret symbol. Yeah, but those are the ways to translate. I mean, we've had some students who they just translate whatever I give in Python into MATLAB. I'm like, okay, all right, if you want to do that, that's fine. But with a few tweaks, and that's what we're here for. We're here to kind of talk about these things. I think you'll find that, hey, I can add Python to my resume by the end of this class. Okay. All right. Other questions on the homework? Okay. All right. So today, what we're going to do, okay, is spend probably another 50, 60 minutes here maybe a little bit extra. And then we're going to all take a walk over to the D wing, and the lab. We have 3 stations, and it's kind of set up for 9 people. Okay. What we're going to do though is we're going to break up. So there's a little lounge in one spot where about 6 people can sit. All right. So 2 teams of 3 will just hang out. All right. And then I'll bring the first 3 teams of 3 in, and the exercise will probably, well, we'll see. I think it'll take about 20 minutes, all right, to do in terms of getting the data, all right? And then tomorrow, the lab assignment stuff is due by the end of class. Okay, so we have the next few weeks before that has to be done for, quote, a grade, all right? But what I want us to do is collect some of the first bits of data from the lab, and so today will just be kind of learning how that works. I think then what we'll try to do is we'll go back to the lab tomorrow, and the team of the 2 teams of 2 will they'll go in first, and they'll do the next bit of experimentation and collection of data, and then that exercise may take a little bit longer. Actually, we'll see, and then yeah, again we'll rotate, and we should be able to get everyone through. So hopefully. This will be a little bit illuminating about the concepts that we're talking about, because if you take the class normally, we just kind of sign up for a lab time and you take it at some point throughout the semester. This way we have the unique opportunity to kind of do the experiments right after we talk about the material. Okay. So what are we talking about today? Well, we're going to be talking about how we test materials. What are the normal axial relationships between stress and strain. Talk a little bit about Young's modulus, or Hooke's law, applied to a material, and the elastic modulus, which is Young's modulus. And we'll also talk about yield strength. Okay. So last time we introduced stress and strain. It was rather rapid fire. And today we're just going to focus on problems that use sigma x, or sigma equals F over A. Okay? So don't worry, we're not going to cover shear stress today. Okay? That will be for another time. We will also cover normal strain today, the epsilon. All right, but this is our focus, F over A. But then we're going to link it to material properties. And it turns out that we use this axial form, this normal loading form, quite a bit when we characterize materials. Why? It's easier to stretch a material in one direction than in multiple directions, okay, at the same time. Okay. Now, has anyone done tensile testing before? Oh, okay. When did you do it?
I do it at work. I was in the process of learning it right before the school year ended.
Okay.
I'll do it again this summer.
All right. So you will be a professional. Well, you are a professional if you've already done this in a work setting, okay? So kind of the purpose here is to put a sample of given dimensions, all right, like these, all right, and with these test specimens, we're going to then figure out what intrinsic material properties are, right? So remember we've talked about this principle of stress now, so that we don't have to build the Eiffel Tower every time and crush it, right? We can take a piece of the Eiffel Tower, which is probably a bad idea too, but you can take a chunk of the material that would be going into your structure and test it, and then have an idea of how it will respond once you give it dimensions, okay? And vice versa. So the standard tensile test is going to relate the normal stresses to the normal strains. Okay? So normal stresses being the sigmas, normal strains being the epsilons. And typically we are going to apply this through some type of mechanical displacement. And we're going to typically try to keep that rate at which we apply that displacement constant. So that means that the strain, assuming the cross-sectional area does not change too much, right? Or even if it does, for strain it doesn't matter too much. Assuming we have an initial length and we apply some change in length to it, we're going to try to keep that rate of change for that strain constant. That's the typical way to do it. Okay, so we also will typically use the original cross-sectional area for these materials. We will talk about something called the Poisson's ratio pretty soon in the class, but anyone that's taken a rubber band, well, maybe not anyone. I should have brought a rubber band. Okay. If you stretch a rubber band, what happens to the cross-sectional area of the rubber band as I stretch it?
Reduces.
It gets smaller, right? You can see it pinches. And for materials like solids, rubber is an interesting material in that, unlike like your fluid mechanics, where we always say, oh, in water, volume is always conserved. Volume is always conserved, right? It's an incompressible material, okay? Unlike a lot of the materials that we use in solids, rubbery materials are actually very close to conserving their volume. The metals that we use actually don't conserve their volume as well, okay? But we don't, it's not a key component or something to think about, right? Because we think about the metals more than we think about rubbery materials in this class. But because we're dealing with these metals, like aluminum and steel, we're going to say that the cross-sectional area is not going to change too much, right? And that's actually true, not true. In the linear regime, it's very true. Once you go plastic, we'll talk about it, like once you start to yield the material, it's less true, okay? And so people will create metrics where they say, oh, this is the true stress or the true strain. But we're going to use the original cross-sectional area, and we're going to call that cross-sectional area A naught, and we're going to then make calculations that we're going to call engineering stress and engineering strain. All right, so the engineering stress, what would it be? It would be the force that I have pulling this thing apart divided by the initial cross-sectional area. Okay. So that's pretty key. The engineering strain, okay, is going to use the nominal length L naught, okay, and that's just going to be what we call delta over L naught. Okay, so here are a couple of things. This quantity right here is the initial length. Okay, this is the delta, that's how much is straining. Okay, but that's not strain, right? Delta has units of length. We've been through this a little bit now. Okay, and so if we go delta over L naught, that's the strain. Now, what is this initial L naught? Is it the distance from here to here? Is it distance from here to here? No, right? It's indicated what it is, right? It's this what we call the gauge length. Why do you think we don't use these other distances? Why don't we use the distance between shoulders or the overall length? Why? Why wouldn't we do that? Why do we specify it? Because we're gonna go to the lab and we're gonna measure L naught. Okay. Why do we do it only in this reduced section?
So we know the cross-sectional area is constant.
We know the cross-sectional area is constant. That's a good point, right? Because otherwise the stress will be different. Okay. Why else? So we know the cross-sectional area there. Yes, Kira.
The larger pieces on the outside are just meant to be gripped and pulled, which means those areas are not going to change a lot and not supposed to contribute to the information.
Right. So those are larger areas. They're being gripped. And I agree with what you said, right? They're not going to affect, right? They're not going to experience as much stress. They're not going to experience as much strain. Okay, they are going to experience those things, but it's going to be lower. Okay. So we're interested in where those larger changes are going to be. Where is the material going to break? Because we're pulling this thing in a lot of cases, not always. We're going to do some experiments where we break it. We're going to do some experiments where we don't break it. But where is the material going to break? What do you think, Shane? In the middle, all right? Why?
Just makes sense.
Makes sense. Isaac, why? You're I see you
like-
thinking.
I think it's because it's probably like the most real. It's like the most thinner part, while most of the materials in the end.
Yeah, right. The cross-sectional area is the smallest in this region, right? So that means the stresses are going to be the highest, right? So it's just like a chain, the weakest link fails, right? So in this case, big link or link with large diameter rings, okay, or something, is where it's the strongest, right? This big, this small, weak, fail. All right, but it may not break exactly in the middle, okay? You're gonna see when we go into the lab. It will not necessarily break exactly in the middle, but it's gotta break somewhere in here. It's what people that wanna sound fancy will say is a stochastic process. Okay, that means there's statistics involved. Yes, it's gonna break at the weakest point, but we don't know. There could be some abnormality or some deformity or some issue with the quality, some impurity, all right, something in there, and it will find it and it will break there. Okay, but it needs to break. You want it to break somewhere in the middle, somewhere in that location where you have this gauge line. The reason also, this is another nuanced thing that you'll cover more in BMC, but the reason that these have arcs here, okay, is because we want to avoid what are called stress concentrations. So another tidbit, when you design a component, all right, it's often a bad idea to put sharp edges in it for multiple reasons. One, milling it can be very tricky to have sharp edges, internal sharp edges, I should say. External sharp edges, you can get those pretty easily with a mill, right? But internal sharp edges, right? The mill has a particular diameter, so you can't get in there. But coincidentally, or maybe not coincidentally, the way the world works, it's actually advantageous that you don't put those sharp corners in, because if you did, that's where you can get a crack begin to open up, and you can get failure. Okay, and that's called stress. That's from a stress concentrator. Usually, stress concentrators are not too big a deal. Not as big a deal with static loading, okay, meaning we go one time. But in the cases where you have vibration or fatigue, where you're going it over and over again, that's where the stress concentrators really play a role. Okay. So, any questions on this? It's like a simple thing. It's a simple idea. Okay. Oh, and I guess also you can see sometimes, right, these go on lathes, and they're made so they're circular, and they have these nice threaded ends that they screw in. And this is like serious business, right? And what you're going to see in our lab, we have kind of rectangular cross sections that have been stamped out, okay, in the shop. Thank you, Mihai. He got them done on Friday for us. Okay, now we have to look at the data. Okay, and this plot is typical for a steel, I should maybe clarify, typical for a ductile steel, maybe typical for an aluminum alloy as well. All right, and we have kind of certain regions of interest, and we get to certain limits or certain thresholds that end up being characteristics of the material. So the first limit that we hit is what we call the proportional limit, but no one really uses that term. We do call it the proportional limit, okay, and I'll say it right now. We also don't really use the elastic limit. I mean, these things are, yes, people know what they are, but you're not going to see them on a spec sheet usually. Okay, so like if you go to like MatWeb or you go to some, you say, hey, material properties of aluminum 6061. All right, it's probably not going to say this is the proportional limit, this is the elastic limit. All right, but I'll tell you what they mean. The proportional limit means that you can go up to this level of stress. Oh, I guess I should have said this earlier. On the y-axis, this is stress. On the x-axis, this is strain. Just in general, if you take multi-physics with me later, simulations, just please say that this is stress versus strain versus saying that this is strain versus stress. Okay? Just the convention we use is that the y-axis is the first thing when we say versus, right? And x is the next thing when we say versus, all right? So it's stress versus strain, and if you're going to be like a scientist, you say that strain is kind of your independent variable, right? That's the one that you're like, hey, that's the one I'm controlling, right? And the dependent variable is going to be the stress, right? Stress depends on the strain in this case, right? That's how we typically plot things. You can plot it the other way around, which is fine, and it's going to have the same meaning. You can flip these axes, but that would not be how people typically look at these charts. So the proportional limit means that you get up to this, as long as you keep the stress in this region, you can have a nice calculation of rise over run. What is rise over run? That's slope. Okay? And it turns out that's something called the Young's modulus, which we'll talk about more. But that's what the proportional limit is. Okay? It behaves linearly. The elastic limit is very close to the proportional limit, typically a little bit higher, and typically not very indistinguishable. Okay? And that's why most spec sheets won't specify it. Okay, but this elastic limit, all right, is kind of the end, all right, of when you can go back down and not have perturbed the material, shall we say. Okay, and what do we mean by perturb? Kind of, and that's why these are very close to each other. The yield strength, okay, is typically around here, which is just beyond the elastic limit usually. So yield means now, once you got into this portion, it typically flattens out a little bit, and so your slope is going to change, and as the material yields, you need to put in less additional stress to get the same amount of yielding, all right, or same amount of strain. Okay, so that's actually flipping this concept of what's dependent on what. But essentially, it strains more easily once you get to the yield. And that's irreversible, okay, once you've gotten there. All right, so the yield stress or strength is given by sigma y, or S sub y. Okay. You'll probably see me do both in the class. The ultimate stress or strength, okay, sigma u or SU, is the peak of the curve. Okay. Now this measurement can be a little bit tricky because once you've gotten into this much of the plasticity of the material, the cross-sectional area is actually changing. Okay? So that means that the cross-sectional area is smaller here, okay, than it was, say, over here. And so if I use just my A naught, I'm probably going to be underestimating what the ultimate strength is. Okay? Because if I had that, if I knew what that new cross-sectional area was, which would be smaller, and I had the same amount of force, right, associated with this plot, I'm going to get a higher value than if I just continue to use A naught. And then finally we get to fracture, okay, out here. And again, right, this is probably, this is probably higher than over here because the cross-sectional area at this point has become significant, at least if it's a ductile material, has become significantly smaller when it finally breaks. A brittle material, we'll talk more about ductile and brittle materials, right? But brittle materials, you're not going to see this type of behavior. When I say this, I mean the plastic, nice long plastic. What you're going to see instead is this. It goes up and bang. That's it. Okay? You see that red line? But a ductile material, all right, is going, and if you're looking at the sample, the samples are going to more or less have this, they're not going to have this necking behavior. This is called necking, this is not necking, right? You're just going to have like a break, okay, between the two pieces. And something like this material, which is absorbing a lot of energy under this curve, yeah, that's a ductile material. So the material, and we'll talk about this, right? Since the behavior in these regimes, all right, in the, like if you're below the proportional limit or below the elastic limit, you're going to be able to go back and forth. Like you can load it, unload it, load it, unload it, and it should return back to its original state. But once you go beyond that, that's when you hit plasticity. But in that elastic regime, it's behaving like it's a spring, so we can also calculate the amount of energy that it stores, right? If I have do you remember the equation for a spring? And do you remember the equation for the amount of energy that you store in a spring? If I know K, you remember what is it? And I know the displacement, what is it?
1/2 kx squared.
Yeah, 1/2 K delta squared, 1/2 Kx squared, right? That's the energy in the spring. Similar type of principle here, right? Usually though with springs, we never say we're breaking them or we're making them yield. You'll do that in DMC as well though, actually. Okay, you'll look at some calculations for coils, and it turns out that the shear stress is what is the problem. Okay, so yeah, it's as we said previously, it's difficult to distinguish between the proportional limit, the elastic limit, and the yield stress or the yield strength. So you're going to typically just write out the yield strength. We have two overall behaviors, elastic behavior and plastic behavior. All right, so this is the plastic regime, this is the elastic regime. This is the plastic regime. This is the elastic regime. Okay, and if you're a designer, you want to be looking at keeping all your materials in the linear elastic regime. We want to be avoiding the plastic behavior, but we want to understand what's going on. And some people love to study this stuff, this plasticity. Okay, it's interesting from both a scientific and an engineering perspective, and there are tricks that they do to kind of delay the onset of this behavior, right, so that you stay in the elastic regime. Okay. Now, remember here we said that there's some slope in the elastic regime, and remember Hooke's law, right? That was the K. Well, 1676 discovers a linear relationship between stress and strain. Okay. From a little bit later, okay, Young is the one that kind of gets his name plastered on the fact that there is a linear relationship. And so he gets attached to the constant. I don't know. Hooke, right? He discovered it, but Young's name is plastered on it. All right. So this Young's modulus is what we call the elastic modulus or the modulus of elasticity. And this is the relationship. Sigma equals E epsilon. Okay? Or EE. However you want to remember it, right? But this is the thing. Alright? You want to write it down on your formula sheet. Okay? And sometimes we think, oh, this is the bomb. This is all there is. If I have material, sigma equals E epsilon. No, not true. Okay? But for a normally loaded, axial loaded system, this is true. Okay? If you have different loads, different configurations, if the material behaves in different ways, okay, then this is not, there's time dependence, there's rate dependence, a lot of those, yeah. But this is the very basic equation, okay. And the units are kind of, how do you say it, evident by these different quantities, or you want to make sure you understand these units. What are the units here? You can't see what I'm pointing at. What are the units here? Yes. Yeah, so that would be force divided by area, and we typically are going to say pascals. Okay. All right. Yeah, okay, Andrew. Anyone else? Okay, what are the units here for epsilon? It's unitless, right? So this one is unitless, right? Because it's some delta divided by some length. So what does that mean the units of the Young's modulus might be? Huh? It's actually just pascals, right? You have pascals on the left and pascals on the right. All right, so this is also going to be pascals. Okay. Now, how do we determine the elastic modulus? And this slide is inspired because I guess someone told our department chair that they went into an interview and they didn't know how to calculate the elastic modulus. All right, so can't say we never said how to do it if it comes up. I have a friend who told me he went into an interview and the guy that came right out after him, or came out right before he walked in, he's like, I couldn't remember the difference between stress and strain. All right, so it's easy now because we're in class, right? It's been 30 seconds since we've talked about it, but these questions, it's just they're accessible to mechanical engineers, right? It's like, hey, sigma equals E epsilon. There are a whole bunch of questions I can ask you to answer that just have to do with manipulating sigma equals E epsilon. Stress equals force over area, and epsilon equals length over length, right? So just I don't know. And then sometimes, right, we've gone through different phases. Like in some companies, they do more technical interviews, and some companies do more evaluations of our psyche, I guess, right? So you don't know, right? But I have been in somewhat technical. Yeah, I've had technical interviews, and you wanna be able to kind of know some of your stuff. I had to do a beam bending thing once it was I had to calculate some stresses in a beam. So anyway, how might we determine the elastic modulus? Well, you're going to get a sample and probably going to give it some cross-sectional area and some length, okay? And we're also going to, I wouldn't even just say, look, do some constant rate of extension. No one's going to really care about that, okay? But you might want to say, oh yeah, it's actually pretty tricky to measure this change in length. You've done some calculations now, right? Remember we were talking about when you hold that roadster or the sedan by that rod, we were talking about the change in length being only the width of a hair. Okay? Well, if you're doing tensile testing, you probably don't want to design your specimen to be such a large cross-sectional area that you can't measure the strain, or you can't measure the change in length. Okay? But nonetheless, it is still tricky to get this done accurately. So there are a whole class of devices called extensometers that you can buy, and some of them look like clips. Okay? The ones that we're just going to depend on the machine, to be honest. So there's a you'll see it in our lab, the Pasco system we use. It just has a set of gears, and they probably have some type of laser encoder inside. I don't know what they have inside, but it's probably just measuring the amount of rotation of something, and that gives us an idea what the displacement is. There are also techniques that use optics and vision. So one of the ways that's become popular is called visual image correlation. Okay, so they take a camera and they actually purposely paint their samples with a bunch of black and white spots. Okay, and then they take video of this, and you can figure out precisely, very precisely actually, what the strain is. Okay, so anyway, but you need to figure out what the extension is. You want to use some type of force sensor. And so there are a whole range of different force sensors out there. And, something that you probably don't think about initially. I'm going too slow. Okay, something you may not think about initially with force sensors is that they do have compliance embedded with them as well. Right? Typically, they have to have some type of element that's straining inside of them, like a spring, and they're also doing some type of distance calculation to figure out what the force is. Then we're going to plot the force versus displacement, okay, or force versus length, okay? Or maybe delta would be better here, all right? Let's just say, okay, we're going to, we got this little L, I guess the way I'm using it here, but, think about it as this is L or maybe delta, okay? And then we got to convert, right? So we convert our stress, or our forces to stresses using the cross-sectional area. We convert our displacements, our deformation to strains by dividing by some initial length. And then we plot it. Here's sigma equals F over A, and we have epsilon equals L over L, and we plot the results, and we look for the linear regime, and it's the slope. It's just the rise over the run. Any questions on that? No? It looks pretty straightforward. Yes?
Is it the rise over run of just the linear portion, or the average rise over run?
Yeah, so we'll talk about this a little bit actually maybe tomorrow, okay? We can come up with some different models, and we'll call it, so one is a linearly elastic, linearly plastic. Okay, so what does that mean? There's a dash in between. So linear elastic would be this regime, and then we could say, oh, we can have another slope that we'll put in for the plastic regime. Okay. But typically, if there's say Young's modulus, boom, stick to the elastic region. Okay. Good. Okay, so here's an example. Let's say you have a 10 centimeter long sample, a diameter of 1 centimeter, okay, and this is going to be in a pretty big machine to do this. Okay, so you measured 10 kilonewtons, and you measured an extension of 60 microns. That's only a hair, not much. Okay. The person who designed this experiment was probably not thinking properly. Oh wait, I know who did it. Yeah. So. So I probably should have used a smaller diameter, okay, or use a larger force, because 60 microns is a little bit tricky to measure, Okay, not impossible, but just a little bit tricky. Okay, so what do? We do sigma equals F over A. We do epsilon equals L over L. And then we say that E, right? So remember, sigma equals E, right? So then that big E is equal to sigma over epsilon. And we can calculate these individual quantities. All right, and we can then write out what E should be, and then if you have the time and the patience, you keep track of all your units very carefully. That's the advantage of doing things by hand. It's not impossible, but it's often a little bit tricky to keep track of the units. The easiest way to keep track of units, though, I'll teach you a little trick. And maybe it's not a trick. Maybe a lot of you already know this. Okay, but easier than Colab, all right, and Bing does okay. All right, DuckDuckGo, I don't know how well it does. I like DuckDuckGo, but I have to say Google is the best at unit tracking. Right? So if you said 10 kilonewtons, right? And what do we say? We have a diameter of 1 centimeter, right? So we do divided by pi times 1 centimeter squared divided by 4. It gives it to you into pascals. All right, and you can say in GPA, and I'll even convert it for you. All right, so this is, if you haven't, how many of you have done this before? No? You've done it?
No shame. Yep.
No shame. All right, good. All right. So, of course, on the exams, you won't have Google to do this for you, right? But this is the easiest way I find. If I got to do a quick calculation, I want to make sure my units are right. This is the way to do it. Okay. Now, this is typically we don't do, like I should have really done it in megapascals. Why? Because this is a stress. Elastic modulus are typically going to be in gigapascals, and I'll have some charts for that later. Stresses are typically in megapascals. Okay. And so what we just calculated here was megapascals. But I mean the stress, right? But if we need to know the strain, all right, we said, oh, what's the strain? It's 60 microns over 10 centimeters, right? So now we can go back into here, all right, and we can do divided by 60 micrometers, okay, divided by, what was it? What did I just say? I can't even remember. 10 centimeters, right? Because we said that stress, right, it's going to be sigma, I'm pointing on my finger, sigma over epsilon, right? So we need the stress over the strain, all right? And so this comes out to be 10 to the 11th pascals, which is pretty high. So I'm going to again do I can do it a couple ways. I can do times 1 e to the minus 9, right? But then that doesn't give me the right units, right? But that's how I would do it on my normal calculator. So what instead I do is I say, okay, I'm just going to say in gigapascals. All right, and so 200 gigapascals is pretty normal. But those like gigapascal numbers are pretty common, I should say. Normal means something very specific in our class, right? But those are common. All right, so that's and you know, but here, look, this is, yeah, this is how you do it in Colab. All right. Why did my numbers not? I must have done something. Did I not divide?
50, but you said 60.
Oh, I used 50? Okay, that's why. I was like, that number's not quite right. Okay, just so. Yes. So, Google still does not eliminate all careless mistakes. All right. Questions? Comments? All right. So this is a nice way to keep track of your stuff. All right, so lots of elastic moduli. Okay. This is steel. Now, something that's kind of fascinating, all right, fascinating, is the elastic moduli of steel and aluminum. They can have different alloys, different types. Their elastic moduli do not change much. Okay? So what you're going to find is that materials can have a wide array of strengths. You can tune the strengths of the materials, right? The yield strength. This is when they start to yield. But as you tune that yield strength, either through heating, through composition, through quenching, through adding actually plasticity to it by adding hitting it with balls or like denting it on the outside, you can change its strength, but the elastic modulus stays remarkably constant. I think, in my head, I always think 210 gigapascals, all right? But here it says 200. Yeah, in that ballpark, okay? Why do I think 210? Because for aluminum, I think 70. Here it says 68. But aluminum, 70 gigapascals, steel, 3 times the elastic modulus. I get 210 or 200, all right? So that ballpark. Other materials of less renown in terms of how we do things with mechanics, titanium. All right, so titanium has an elastic modulus around 116. That is not something that I think of every day. Okay, I also, unfortunately, don't think of wood, okay, a whole lot either. Okay, but it has elastic modulus around 10. And these other materials, these polymers, right, they have kind of a wide range of elastic moduli. So those do get tuned quite a bit. Their elastic moduli do, okay? But they're different polymers. And rubbery materials, all right, 0.01 to 0.1, even less than that, okay, in some cases. I would consider them to be rubbery. This is in our small strain for whatever rubbers they were looking at. Okay, so the elastic moduli to remember: steel, titanium, not really. Wood, also not really, but sure. Thermoplastics, sure. That's probably that's a good number. Say plastics, just give it 1 gigapascal. And rubberies, yeah, like a tenth or a hundredth of that. A couple of classes, I made deals with them. The first question on the final exam, if you look at, actually I don't know if I have those final exams posted. First question on the final exam will be, what is the elastic modulus of aluminum? All right. Or what is the elastic modulus of steel? Okay. I don't know. You don't, just write it down somewhere. Okay. Back to this strain in a bar holding a roadster. All right, we've got the opportunity, okay, to think about both the strain and the stress, right? So remember, we were talking about scaling laws when I first introduced this, when we first talked about this bar hanging, or the car hanging from the bar, okay? And we just said, oh, if I change the diameter by a certain amount, in particular, if I double the diameter, right, that's going to quadruple the amount of supportable load, we said, right, because it goes with the area. So now, I wasn't lying to you completely. Okay? We can do things like, hey, what's the strain, right? We had a K here before, right? But what's the strain? We can calculate it if we know the K. We can, or if we know, or if they tell us what it is, right? But if we know the K, right, we can calculate what the strain is, or we can calculate what the displacement is, and then we can calculate the strain. We can calculate the stress. Stress doesn't care how long it is. All right, and we talked a little bit about that too. Remember, we said stress or the strength doesn't really care how long the sample is. How much it deflects cares about how long it is, but the stress or the strength of the material does not. And so here we can calculate the stress. And now, what is the elastic modulus? Well, what do you think I designed it to be? Any guesses before it magically appears? Right? I gave you a steel bar. And so the steel bar has an elastic modulus of 210 gigapascals. What did I do to create that prior problem? I had to work backward. Right? I said, oh, if I'm going to make a bar and I'm going to hold a car with a bar, probably use steel. And steel, well, I'll say has 210 gigapascals. Then I put in the dimensions of the bar and I said, that's what the spring constant has to be. Okay, it has to be that because that's the elastic modulus of steel. I could have put in elastic modulus of 70 gigapascals, right? And then I could have figured out what the appropriate stiffness would have been. And because I know the elastic modulus of aluminum is 1/3 that of steel, then if this had been an aluminum bar instead of a steel bar, my K would be 1/3. Okay, if it were aluminum, and so that would have been, I don't know, something like 80. Not 80, 60, 50 something. All right, like that. Kilonewton per millimeter. Anyone know why people ride aluminum bikes?
They're lighter.
Yeah, right? Aluminum has a lower elastic modulus, right? But its density, anyone know what the density of aluminum is? Fun times. Okay, anyone know the density of steel? All right, well, these are not necessarily things that would run off the top of your tongue, but maybe they would. Like steel, typically around 7,800 kilograms per meter cubed, and aluminum typically about 2,700 kilograms per meter cubed. Okay, so, yeah. The ironic thing about aluminum bikes is that they actually are stiffer. Is that if you've ever ridden, well, you have larger cross-sectional areas of the tubes, and so they typically are very stiff. They don't bend as easily. Okay, whereas the steel bikes, they have narrower tubes and they typically do bend a little bit more easily. And then you have people who ride composite bikes, right? And we have composite. We won't talk much about composites in this class, but they really are. When I say composites, what I mean like glass fiber reinforced epoxies, okay, or carbon fiber reinforced epoxies. These are Kevlar reinforced epoxies. They're amazing, right? They've changed the aerospace industry. Okay, so now if we wanted to do that thing that I just said, which was figure out what the spring rate or spring constant is for a given elastic modulus, right? So this is what I had to do when I made that problem. Let's take a look at Hooke's law and let's see if there's some relationships that spill out. Okay, so stress, I know, is force over area. Strain is delta over length. Okay. So another way to write this is to say, okay, F over A has to be equal to E times delta over L. And now I can say that the elastic modulus is going to be FL over A delta. Okay, so that's one relationship. And if I rearrange things a little bit more, so now I kind of come back here. This is maybe not the most efficient way to get there, but we can say that the F over the delta is K, all right? And so F over delta, right? So that, so I just put a K up there. All right, you see that? And E is equal to KL over A. This is a nice relationship, and this is the relationship like I could manipulate, right? I knew I had an area, or I knew I had an elastic modulus for my material, and I wanted to figure out, okay, let's take a length, and then that means I can pick an area, you know, or I can pick an area, and then I can pick a length for the spring constant, right? So this is a pretty popular one, okay? And this is the most popular one. Oh no, that's, well, more popular than the other one. K is equal to E over A, EA over L, and this is the most popular one. Delta is equal to flea, all right, or plea, all right, FL over EA. So if you're given a bar that has some length, has a cross-sectional area, and you're given a force, and you're given an elastic modulus, you can figure this out. This is in a year or two, when I have students, this is like the only thing they remember from the class. Maybe not the only thing, but this is like, it's like, no, not every answer is flea, okay? That's not the answer to all questions, all right? But it is important for bars. Okay. And there's the box. Okay, I'm going to, I think these are pretty straightforward. Let me just look here. Yeah, these, so the biggest thing is going to be the units. So when you do these problems, you see, because we've got kilonewtons, we've got microns, we've got centimeters, right? I suggest either keeping track of them on paper, keeping track of them in Colab, or keep track of them in Google. All right, but keep track of them. This problem, it's about calculating out the elastic modulus. There's the answer, I guess. All right, but you should be comfortable with this. And if you look at previous exams, you'll see, boom, there's a plot. Please tell me what the elastic modulus is. Okay, this one, all right, you might, and this one there are 3 problems. So this I do think is nice to do in Colab, but you can do what you like. Okay, the first question down at the bottom is asking what is the stress in the cables. There are 2 cables, which means that the cross-sectional area is double 1. All right, so you have the mat, the volume of this times the density. The density is given as 1,000 kilograms per meter cubed, which is about right. That's like water, okay? Which is not far off, right? And then you know the height, the width, and the thickness of this sheet, right? So width times height times thickness gives you a volume, times the density will give you a mass, times the gravity, or the constant due to the gravity. That gives you a force in newtons. Note this is 1 centimeter, this is meter, this is meter. So, you know, make that 0.01 meters. All right? So you figure out what the force is, and then you divide by the cross-sectional area. Right? And the cross-sectional area is going to be twice that of an individual cable. Right? And how do you figure that out? Well, the cross-sectional area was given as 0.1 centimeters squared. So again, that's a kind of a crummy unit. Right? But 100 centimeters times 100 centimeters gives you 1 meter squared. Okay? So anyway, so you can figure out what the force divided by the area is, and that's what your stress, or force divided by twice the area is going to give you the stress. Okay, the next question is, what is the strain? And note, I think the previous question, did it give? Yeah, it gave an initial length, but you didn't need that length when you're calculating stress. Right? That's one of the points here, is that you don't need to know how long the bar is to calculate what the stress is. Okay, this one is, what is the axial strain? Well, a nice way to do this is to say that you have sigma equals E epsilon. We didn't use E prior either, okay? That's the elastic modulus. So now, if I want to figure out what the strain is, I say, well, sigma equals E epsilon. That means that strain is going to be equal to sigma over big E. So I already know how to calculate the stress. So I say the stress divided by this, which is in gigapascals, so another big unit. And that would give you the strain, but it's a microstrain. Okay, so that means that you have to multiply by 10 to the 6. Okay, so that's how you do that. And then the last question is, what is the change in length? All right, well, there are multiple ways to do this, but one way is simply strain is equal to change in length over L, right? So if strain is equal to change in length over L, then I can say, oh, well, the change in length is going to be equal to just the strain times that initial length. Okay. Again, if you calculated it out previously in microstrain, just be careful here. But that's also not, that's not bad because they want us in units of micrometers. Okay, so again, be careful. Micro 10 to the 6th. And sometimes it's useful to say, oh, it's like I have 1,000,000 microns in 1 meter. So that helps you figure out if you have to multiply or divide by 10 to the 6th. If I had indeterminate loading, which is, not as friendly as some of these other problems we've discussed, but you can go back to session 3 where we calculated out what the internal forces, okay, are going to be in these two members. Right? Indeterminate loading means that we had an extra constraint, or we had a constraint that meant that there were more unknowns than there was one equation of equilibrium. So we have two unknowns, the reaction forces, and these reaction forces F1 and F2 are what we have as internal forces for these two members as well. Okay, so if we calculate out these internal forces, right? So this is a collab that does that for these parameters that are given. We can figure out what the stresses are in both of these sections. Okay? And we can then figure out what the strains are. So given this, the known material, right? So so the stresses, they don't care what kind of material you're using. In this region, they're going to be tensile. Okay, tensile meaning it's going to be pulling it apart, right? So that's because it's pulling it this way. Remember, it's coming out. This force is going to be pushing it in, so it's going to be negative. All right, so it'll be a negative stress. Okay. So sigma 2 should be negative. Should be negative. I was waiting. Oh, there it is. It finally appeared. Okay, that was weird. It took a while, but it's negative. Okay. The length, okay, is going to help us calculate out the spring constant if we want, or we can use it to calculate out something just happened. Oops. Yeah, something just happened. Okay, we can have and so we can relate the length to the elastic modulus area in K. All right, and the strains. So the reason I made a boo-boo the first time, it's because it's already negative here. Sigma 2 is already negative. So if I want strain, I don't have to multiply, or I don't have to use a negative on a negative. Okay, it's just still this negative stress divided by E. So that's how you handle this. All right. Yeah, this is good. I think we're pretty much. Let's skip this. We are going to. Should we? Yeah, maybe we'll. We're going to talk about. We'll talk about this next time. All right. Yeah. Actually, in the lab, Should I say it? We'll talk about it next time. In the lab, we'll talk about it in the lab too, a little bit. Okay. All right, so that concludes this. Let's pack everything up. Give me a couple seconds so that someone doesn't steal my stuff. And then we'll head to D123K. All right.